Hello, my name is Tom, and today I'm going to be talking to you about capacitors in DC circuits. Firstly, what is a capacitor? A capacitor is an electronic device that stores energy in the form of an electric field. The most basic construction of a capacitor is two conductive plates separated by a dielectric material. The capacitance is a measure of the size of a capacitor and is usually measured in farads. This can be calculated in two ways. First is equal to the charge divided by the voltage, and second is equal to a universal constant times the area of the conductive plates divided by the distance between them. The amount of energy stored in a capacitor is equal to half times the capacitance times the voltage squared. Note, most capacitors have a value in the range of microfarads. Capacitors in circuits are represented by one of the following two symbols. When multiple capacitors are connected in series, the total capacitance is equal to 1 on the capacitance of the first plus 1 on the capacitance of the second, and so on. While capacitors in parallel are a lot more simple, being the total capacitance equal to the first plus the second plus the third, and so on. To analyse the capacitor's behaviour in circuits, first you need to know about the time constant. Represented here by tau is equal to R times C, where R has to be the Thevenin resistance of the circuit and C is the capacitance. An example is given here if you wish to pause the video and work your way through it. Now we're going to look at the voltage across the capacitor during the charging phase. At any point in time, the voltage is equal to the maximum voltage times 1 minus e to the minus t on tau, where t is time and tau is the time constant. As shown here in the graph, initially there is no voltage across the capacitor, and after a period of 5 time constants, the maximum voltage is reached. Now for the current in the charging phase, where the current is equal to the maximum current times e to the minus t on tau. Once again, t equals to time and tau equals to the time constant. As the graph shows, initially there is the maximum current going through the capacitor, and as time goes on, the period of 5 time constants slowly goes down to 0. Once a capacitor is fully charged, it is considered to be in steady state. This occurs after a period of 5 time constants has passed. During steady state behaviour, a capacitor can be considered to act like an open circuit, and all other calculations are done as normal for DC circuits, by replacing the capacitor with an open circuit. Now for the voltage during the discharge phase, where V at any point in time is equal to the maximum voltage times e to the minus t on tau. This graph acts like the current during the charging phase, initially with 100% of the voltage, and after 5 time constants, no voltage through the circuit. For the current during the discharge phase, it is the same as the charging phase, except the current is negative. This is to indicate that the current now flows in the opposite direction than during the charging phase. That's it, thanks for watching.